Hopefully you were able to put those in order and at least work out what some of those reactions are. If not, you might want to look back at some of your Year 9 material, so rusting, thermal decomposition of metal carbonates, all of that, and combustion as well, all of that's on your Year 9 curriculum, which you did last year. We're going to think a little bit now about what we mean by rate of reaction. I think you could probably have put those in order, thinking about, I think you probably thought about time and said that, well, it takes a long time for the rust to appear, so that's a slow reaction, whereas the bright light in the fireworks appears immediately, and therefore that's a fast reaction. So immediately we know in our heads that rate of reaction is going to be something related to time. I want you to think though as well how you could see that a reaction has happened. So if you think about the egg, when you cook an egg, the whites of it, the white of it is to start with transparent and colourless. And you probably thought about when the reaction was done by thinking about when the white of the egg turned white and opaque. And that involves a change in a product, in an amount of product. With the thermal decomposition of copper-2 carbonate, to work out the rate of reaction, you could think about how quickly it turned from green to black. And again, that would be about working out how quickly the green copper-2 carbonate disappeared, how quickly the black product, the copper oxide, appeared. With the fuel, you could measure how quickly the fuel disappears, so how quickly the reactant is used up, so it would become nothing at the end because the products are carbon dioxide and water, which is produced as steam. So hopefully you can see that rate of reaction involves something to do with an amount of product and something to do with time. So rate of reaction tells us how fast reactants are turned into products, and every reaction involves reactants on the left, an arrow, and then products on the right. But we've got this formal definition that we need to learn, so I'll jot this down in your notes. Rate of reaction is change in amount of product or reactant divided by time. And let's just have a quick think about what this might be. So change in amount of product could be, for example, a mass of product. So could be, you could measure a solid, in which case it would be in grams. Or it could be a volume of gas in centimeters cubed. And then time is usually going to be in seconds, because reactions that we study in the classroom are usually fairly quick. So rate of reaction is going to have units, which is some kind of amount, e.g. grams, divided by time, so per second, grams per second, or it could be centimeters cubed per second, or something else. So it could be litres per second or kilograms per second, but you need to have an amount divided by time. Let's think about a quick example of how you could measure easily a rate of reaction. Imagine that you had magnesium ribbon in hydrochloric acid. You hopefully know this reaction again from Year 9. Metals react with acids to form salt plus water. So magnesium solid reacts with the HCl aqueous to form, metals plus acid goes to salt plus hydrogen. I think I might have said water, to form MgCl2, that's the salt, plus hydrogen. Okay, let's just balance that up. Make sure you know how you get the formula of magnesium chloride. So magnesium is in group 2, chlorine's in group 1. So when you switch the numbers around, you get MgCl2. Okay, and you should know hydrochloric acid. Now, if we look at this, the solid is gradually disappearing. Okay, it's dissolving into the solution. So you probably would intuitively be able to say, well, we could time how quickly that magnesium ribbon disappears, and that would tell us what our rate of reaction is. So let's imagine our reaction. Let's say that we had a stop clock and we timed that it took, let's say, 1 minute 30 seconds, or let's make it 35 seconds, for the magnesium ribbon to disappear. We would also need to know the quantity of magnesium ribbon we had. So let's say we weighed our magnesium ribbon, mass of magnesium ribbon before we did the reaction, and it was 1.24 grams. Okay, our rate of reaction therefore would be the change in amount of reactant or product. Well, we're looking at a reactant, the magnesium ribbon, and we're looking at its mass. So it'd be 1.24 grams divided by the time. Now, 1 minute 35 seconds, time is always a funny one. It would be better for us to put that into seconds. So that's 95 seconds. And then all we do is put that through our calculator in order to find the rate. I don't have my calculator on me, so you'll have to calculate that value. But we will get a value which we would put to 3SF, and that would be measured in grams per second. Okay, because our units were for mass were grams and our time was in seconds. And that would tell us how fast the reaction is. But actually there's a better way to do this one, because the reaction produces hydrogen gas. So we could measure the volume of gas that's made. So let's say that we had, on here it looks like we have got about 40, let's say 48 centimeters cubed of gas produced in, let's say 30 seconds. Our rate therefore would be 48 divided by 30. Okay, so our change in amount, this time of a product, our volume of gas, divided by the time. And this time our units would be centimeters cubed per second. Okay, and then again we'd have an alternative value for the rate of reaction. Now the reason this way of measuring the rate is better is because you can actually monitor how the rate changes over time. Let me show you. So on here we could actually measure the volume of gas produced, say, every 10 seconds, and we could plot a graph. So let's put on our x-axis time. So that's the independent variable, the thing that I'm selecting. So I'm choosing to measure the volume of gas every 10 seconds. And on the y-axis, I would have the thing that I'm measuring, which is volume of gas in centimeters cubed. Okay, and I could plot my graph. So maybe every 10 seconds, so 0 seconds, 10, 20, 30, etc. And let's just think about what would happen during the reaction. Initially, there would be no gas. Okay, so let's say this is 10 centimeters cubed, 20 centimeters cubed, 30, 40, 50. So initially there'd be no gas. So it would go through the origin 0, 0. And at the end of the reaction, there would be no more gas produced. So we said there was 48. So I'm going to put 48 here, across here. And every 10 seconds, well, it's going to stay at that level, isn't it, if the reaction has finished. And then in between, well, initially the gas would be produced very quickly, but gradually it would slow down. Okay, so here's my line. That's actually not the best line. Let me try again. Here's my line. That's better. Okay, so imagine that I'd measured these quantities. And the gradient of the line tells us the rate. Let's think about that. The gradient is how steep the line is. At the end of the reaction, the rate is 0. Yeah, it's finished. The rate has to be 0 at the end. Whereas at the beginning, it's very fast. Rate of reaction equals change in amount divided by time. And I think you have done gradients in maths and know that it's change in y divided by change in x. The gradient of a line is change in y over change in x. Well, the change in amount of product, the volume of gas, is on my y-axis. Okay, so gradient change in y over change in x equals volume of gas, that's on my y, and on my x, time. Well, volume of gas divided by time is rate, isn't it? Change in amount divided by time. But we've got a curve, so it's much harder to work out the rate, and we have to draw something called a tangent, which I think you also will have come across before. So imagine this is my graph. So we had a curve that looked a bit like that. We had time and volume of gas. And I need to work out my rate at each point. And what I do is I draw something called a tangent. So say that I want to find the rate at, so here was 0, 10, 20. Let's say I want to find the rate at 20 seconds. I go to the point at 20 there, and I draw a straight line that shows the gradient of the curve at that point. So the distance from the curve should be about the same on either side. That distance is about the same. And I make that into a triangle because I can find the gradient of a straight line. So I do my triangle, and then I just do gradient equals change in y over change in x. So change in y is that distance, and I can read off the values on my y-axis. I haven't drawn the values, but you could do this. Divided by change in x, which is here. And again, I just read off the values. So I go to my axes, read off the values, and I get the gradient, and that is the rate at that point. I can also work out the average rate over a period of time. So the average rate over a period of time is actually very straightforward. I just work out the change in amount of product over that time period and divide by time. So say I wanted the average rate over 50 seconds. Okay, I'd find my point at 50 seconds. I'm going to do this in a different color now. So 50 seconds, my volume, I read off the graph. So let's say that's 70 centimeters cubed. And the time that's passed is 50. So average rate over first 50 seconds is change in amount, which is 70, divided by time, 50. And then that gives me a value and the unit, centimeters cubed per second. So we've got two different types of rate that I can calculate. Firstly, the rate at a particular point by drawing a tangent. So that's the tangent one. And secondly, the average rate over a period of time. And I'm going to get you to now have a go at doing these for yourself.